This video will be discussing graphing rational functions. I am going to identify the holes, asymptotes, x-intercepts, y-intercepts, domain, range, and end behavior of each based off of the directions. And I'm going to graph once I'm finished. So when you're trying to find your holes, what you want to do is look for the factor that's the same in both the numerator and the denominator. You're going to set whatever that factor was equal to 0. You're going to solve for x. And then once you do that, you want to go back, substitute that x value into your remaining problem, and then solve for y. When you do that, your remaining problem is key. You don't want to include your holes. Y actually goes with your horizontal asymptote because on a graph, you have either an x-axis or a y-axis. And so you might get confused. The horizontal or the vertical asymptote goes with x or y. This was my way of helping you to remember that horizontal and y go together. So a hungry horse ate hay horizontally. All of those H's, and then H-A-Y spells hay. And that's going to be important because when it's time to do your vertical asymptote, that's no longer y. That's going to be x. So back to horizontal asymptotes. You have 3 rules to follow. So if I am giving a rational function and my top polynomial is represented by p of x, and which is my numerator, and then my denominator is represented by q of x, what I'm checking for is the degree, which is also known as the power or the exponent. And I'm trying to see which one of these rules I'm going to pay attention to. So if my numerator's degree is larger than my denominator's degree, then my horizontal asymptote is going to be none. If my denominator's degree is larger than my numerator's degree, then it's going to be y equals 0. The exception would be if there is actually something out to the side, say for instance, plus 5, I would now add 5 to that 0. So 0 plus 5. Or if it said minus 3, then it would be 0 minus 3. And then the last rule would be if the degree of the numerator and the denominator are exactly the same, what I'm going to refer to is my leading coefficient. And again, if I had something to the side, I would still include that information as well. So now what I want to do is go down to vertical asymptote, which I just mentioned is now going to be set up as x. But in this one, what you want to do is you want to set your denominator equal to 0 and then solve for x. And again, you don't want to include your holes. So it would make more sense to go ahead and make sure you solve for your holes before you start doing other things, because you're not going to include them when you're trying to find like your vertical asymptote or your x-intercepts. And that's the next one. The x-intercept, instead of the denominator, we're going to set the numerator equal to 0, and then we're going to solve for x. And again, you only use what's remaining. You don't include your holes. Your y-intercept, you can go back to your original function, and then you're going to replace all of your x's with a 0 because we know for y-intercept, your x has to be 0. And then you're going to solve for y this time. You can also do a lot of these in the calculator. You can just go to your table and look for this information that will help you out. What you think is supposed to be verified in the calculator. Slant, oblique, asymptote. So that one requires you to use long division in order to find it. It could be an equation. And then what's going to happen is you don't use the remainder, but you're going to actually use that information to help determine your end behavior. Just as if you had a horizontal asymptote, you would use that to determine your end behavior. When you have a slant or oblique asymptote, you cannot have a horizontal asymptote, and vice versa. If you have a horizontal asymptote, you can't have a slant asymptote. You can, however, have a vertical asymptote and a slant asymptote at the same time. When I'm looking at my graph, let's just say, for instance, I have a horizontal asymptote up here and maybe a vertical one this way. I'm just making something up. It's not necessarily accurate. If my graph is going this way and this way, what I'm looking at is the arrow that's closest to the horizontal. Make sure it's horizontal, the one with the H, asymptote. So as x is approaching positive infinitive, these are my x values, right? So as it's going this way, what's going on with this arrow? If I try to, it's my y. If I'm trying to go as f of x, because that's what it's going to say, what is happening to f of x? If I try to straighten this arrow down to make it, because y, f of x is either up or down. So if I try to take that arrow and straighten out this graph, it's going to hit at this asymptote. Let's just say that asymptote was 2. So that is what what I'm going to put in the blank. As x approaches positive infinity, f of x approaches, and then I would put my horizontal asymptote, which in this case was 2, right? Same thing on the other side. If I am looking at the arrow that's closest to my horizontal asymptote, and I know that this time my x is approaching negative infinity, so x is going this way. What is going on with my y if I were to stretch that arrow up? It's going to still hit that horizontal asymptote. So if I have a horizontal asymptote, I'm just going to put that in the blank. Now, if I have a slant asymptote, I have to pay attention to that one because that will probably be negative infinity or positive infinity. You can double check it by using your calculator, and I put the notes over here. You can go into your table set and just put like a number that represents negative infinity. I usually use negative 10,000, but you can use negative 1 million. It doesn't matter, just a big number. And then you go to your graph, your second graph, which is actually your table, and look for the number that's shown in your Y column. And if it's a horizontal asymptote, chances are that's what you're going to see, the same number. Or you're going to see something that you might need to round. So for instance, if it's 0.999, that simply means 1. If it was, let's just say it was 2.5 e negative 10. Well, that's a scientific notation telling you to move your decimal over 10 places. And when you do that, guess what? You're going to have to fill it with zeros. So this is really 0. So I have 2 examples that I'm going to go through. So let's go ahead and use the rules that we just said that we're going to do for wholes. So I would personally factor it so that I can quickly see if the numerator and denominator matches. F of x is also known as y. So I'm just going to change it to y since we're talking about the graph and we have x and y axes. So y is equal to x minus 2, and that's all one expression. So I'm just going to leave it in parentheses. And when I factor the denominator, I have 2 as my greatest common factor times the quantity of x squared minus 4. I notice that's a difference of 2 squares, so I can continue factoring. So that's what I'm going to do. And I can just bring this over. 2 times x, the quantity of x plus 2 times the quantity of x minus 2. So like I said, for your wholes, what you're looking for is where the numerator and the denominator have the same factor. So I have an x minus 2 up here and an x minus 2 up there. I want to scratch through it because I know when I go back to substitute, I don't want to include that. So what I have to do in order to actually find my coordinates or my ordered pair for the wholes is to solve for x first. That's going to be this first spot. And then the second spot is your y. If I set it equal to 0, what would have made that equal 0? So it's the opposite sign. Instead of negative 2, which is already shown, is positive 2. I notice in my numerator, everything is gone. So what I have to do is replace it with a 1. So once I replace that with the 1, and that's important because that's part of my answer, I'm going to have 1 over 2 times, well, this time instead of putting an x plus 2, I'm going to replace that x with the 2. That is going to be 2 plus the 2 that's already shown in the denominator. Once I simplify this, 2 plus 2 is 4. And since that's in parentheses next to the 2, that just tells me to multiply it. My y becomes 1 over 8. I personally like it as a decimal. So 1 over 8 is going to be approximately 0.125. That's what I'm going to use as my y. So if I'm graphing, I have to pay attention to this because this is going to be represented by an open circle instead of a closed point. So that's what a whole looks like. I also want to pay attention to these 3 because that's going to be my restricted values for, or my excluded values when I'm talking about domain and range. So for my horizontal asymptote, that is the one that had the 3 rules based off of my degrees. If my degree in my numerator is smaller, in this case, than the degree in the denominator, it's going to automatically be 0. So my horizontal asymptote is going to spell the word hay. So y, H-A-Y, is equal to 0. And as I said before, if there was something to the side like plus 3, I would have to add that 3 to that 0. For my vertical asymptote, what I want to do is I want you just look at my denominator only, what's left over. So I'm going to go back to this portion right here. So what's left over in my denominator, set that equal to 0. Do not include the part that I scratched out. When I set that x plus 2 equal to 0, then that tells me that my vertical asymptote is going to be, this time it's x. X is equal to the opposite sign, which is negative 2. I said in my notes that if I have a horizontal asymptote, which I do, that means I cannot have a slant asymptote. So I'm going to write the word none. My x-intercept means that my y has to be 0. My y-intercept means that my x has to be 0. So I can go ahead and set that up. For my x-intercept, if I am doing it manually, I go back to the part where I scratched out my holes and I look at the numerator only. So my numerator just has a 1. That means I'm not going to have an x-intercept. Another thing you can look at is if your horizontal asymptote is 0, then by default, you won't have an x-intercept, because that's telling you when y is equal to 0, that means that the x-axis is off limits. So there's no way I'm going to be able to have an x-intercept, because x-intercept means, well, where is the graph intercepting the x-axis? And the same would apply if I had a vertical asymptote where it said x is equal to 0, then that would mean I would not have a y-intercept. This case, I do have a y-intercept. All I would have to do is go back to my original problem if I wanted to use the manual math versus the calculator. And in my original problem, just substitute every time I see an x, I want to replace that with a 0. And what's going to happen is just going to go away. 0 minus 2, which is negative 2. And then 0 squared is 0. 0 times 2 is 0. And then 0 minus 8 is negative 8. If I simplify this, this becomes positive 1 over 4, which is approximately 0.25. So that is going to be my y-intercept. For my x values, the ones that I highlighted for my restricted values here, I'm going to highlight in green. That will tell me that that's going to go with my domain, because my domain represents my x values. So for my range, those are my y values. And again, only these restricted values, that's all I'm looking for. These are going to be my y values. So now what I want to do for my domain is I'm going to say all real numbers except what I just highlighted in green above, and put it in the order that it comes on the graph from left to right. So except negative 2 and positive 2. If I am writing it with interval notations, then I would always start with negative infinity, and then I would go to the first number that I cannot go to, union, take that same number, and then go to the next number if there's one, union, take that same number, and now I can go to positive infinity, because my graph always starts from negative infinity and it goes to positive infinity. And then the same from the bottom to top, negative infinity to positive infinity. That's just how it will always work. And then what I want to do is I want to go to my range. My range is going to be all real numbers except what I highlighted in blue. And again, going from left to right, 0 and 0.125. Interval notation, always start with negative infinity to 0, union, 0 to 0.125, union, 0.125 to positive infinity. Now my end behavior, what I'm going to do is always go back up here and see if I have a horizontal asymptote, and I do. That's going to be what I'm going to use, 0 and 0. Let's go to our graph and let's try to graph what we can. I already put in the horizontal asymptote, and now my vertical asymptote is going to be where x is negative 2. So I'm going to use my ruler again and go to where x is negative 2, and that's where I'm going to draw my vertical asymptote this time. So I have these two accounted for, my horizontal asymptote, my vertical asymptote. Now I want to go and do the whole, which is at 2 and 0.125. So somewhere in here, I'm just making it big because it's kind of hard to see an open circle in this little graph. So I've accounted for that. And now I'm going to go to my y-intercept, which is 0.25. So that's accounted for. I didn't have an x-intercept, which means it's not going to touch the x-axis at all. So now I can just go ahead and connect as best as I can. I can get really, really close to this asymptote without touching it. Go through that point and go up and go really, really close without touching it. If you want it to be accurate, just go to your calculator's table and then you can get some points. So that's what I'm going to have to do to get the other side. So I've already put in the problem, and then all I have to do now is just go to second and then graph, and I can pick any points in front of my vertical asymptote. So my vertical asymptote is x is negative 2. So when I'm looking at my calculator at negative 2, I see an error. So that tells me I'm on the right track. So it's either going to be an asymptote or the x portion of your whole. So that's what you're looking for. So if I go down to positive 2, I see see that's the X portion of my whole. So back to trying to find points. I could use -3 and -0.5, or I can try to keep going up and try to find a whole number. Doesn't look like I'm going to find one. So that's good. I can just use that, any of these numbers that are before that vertical asymptote. So let's go to -3 and then -0.5. And of course, it's not going to be perfect. And now, because I have that point, I know I can get really close to my vertical asymptote and really close to my horizontal. And that's my graph. Let's verify that I did that right. So again, go back to the calculator, hit graph, and this is what my picture should look like. The only thing that will not show on this calculator are the holes and the asymptotes. But I can see, just looking at it horizontally, yes, that asymptote is definitely on the x-axis. And as far as my vertical asymptote, I can see where both of the graphs are going vertically. It's going to be somewhere in between there, and it looks like it's at -2. So in terms of my end behavior, if I go to second window, see where it says table start is -11, just change that. If you want to start with your negative infinity first, change it to something like -10,000, and then just immediately go to second graph, which is your table. And you'll notice it has in my Y column -5, and then it has the scientific notation, the e to the -5. This says -5, e, -5. So it's asking me to take it and move it 5 places to the left. And then I would just put zeros there. So this is really 0, which is the same as my horizontal asymptote. For example, 2, we're going to do the exact same thing, except we're going to go ahead and we're going to factor this first. So it looks like that I do not have any holes. So what I'm going to write is none. Well, how do you know? Because nothing looks the same. This is a -3. This is a +3. So they are not the same. So now if I go down to my horizontal asymptote, I see, if I'm looking at my degrees, I don't have a horizontal asymptote because the numerator's degree is higher than the denominator. That would be none. So when I see that, chances are I might have a slant asymptote. So I'm going to look out for that. How do I know? Because the slant asymptote, and I forgot to write that part in the notes, so I'm telling you now, has to be where the numerator is exactly 1 degree higher than the denominator. So you're going to go back to when we were using the long division of polynomials. Fraction means divide. So you take what's in your numerator and put x squared plus 2x minus 3 on the inside, and it's divided by -4x plus 12. You take your first term of your dividend and divide it by the first term of your divisor, and that's how you get started. So I'm going to have x squared divided by -4x, which is -1/4x. So I'm going to take that and I am going to place it above my x. Then I take that -1/4x and multiply it times everything that's in my divisor. So -4x times -1/4x. Well, the -4's go away and I'm left with x times x, which is x squared. So that's what I'm going to put here, x squared. And then I take that same -1/4x and I multiply it times 12. Well, 12 divided by -4 is going to be -3x. So now I go back and this is an expression. I'm going to change the signs. So that's a -x squared once I distribute it. And then this is going to become a +3x. And now when I simplify, I end up with 5x minus 3. So what I want to do is start the process again. Take the 5x divided by the -4. The x's go away and I am left with -5/4. -5/4. This is my slant asymptote. It's an equation. So that's what I'm going to write this, and notice it takes on the y value. Y is equal to -1/4x minus 5/4. And then I'm going to go back and I'm going to look at my vertical asymptote, which is what's in my denominator. I don't have any holes, so I don't have to worry about that. So that x minus 3, set it equal to 0, and that is going to become a +3. But I don't just write 3. I write x is equal to 3. My x-intercept tells me that I have to have a 0 for my y. My y-intercept tells me I have to have a 0 for my x. So I am looking at my numerator, which does not have holes, and I'm setting each factor equal to 0, and that's going to give me my x-intercepts. I have 2 x-intercepts in this case. So I have a -3, which is the opposite sign that will make that equal 0. And I also have a +1 and 0 because that is what would make that 0. So remember zeros, roots, solutions, that's what this is. So that's my x-intercepts, 1 and -3. And then for my y-intercept, if I went back to my original problem and I replaced all of these x's with zeros, that's going to leave me with -3/12, which is the same as -1/4, which is the same as -0.25. This is what I'm worried about. Those are my restricted values. So if I have an x, that's going to go as a restricted value for my domain. If I have a y, which I don't, my domain, all real numbers except 3, because that is a restricted value. I don't have a restricted value for the whole or the horizontal asymptote. So this would be an interval notation, negative infinitive to 3 union 3 to positive infinity. In terms of my end behavior, this time I don't have a horizontal asymptote. So I have to graph it so that I can see if it's negative infinity, positive infinity. All right, so I'm going to go to my y equals, something's there, hit clear. Anything that's in the numerator, I want to put it in parentheses. Make sure you're using the negative that's next to the decimal, and then put that in parentheses. Double check it, make sure that you entered it correctly. I'm going to go back to my windows because I left this at -10,000. So change it to 0. And now if I go to my table, I have reasonable numbers. If I go to 1, I have a 0. So that was correct on my x-intercept. And if I went to -3, I should have a 0. I do. If I go to 0, I should have a -0.25, which I do. That's my y-intercept. I should have an error for 3, which is my vertical asymptote. Awesome. That's good. So I'm on the right track. Now, if I want to see what the graph actually should look like, this is what it should look like. I'll put the slant asymptote formula in also so I can graph it. But for now, I'm going to go back here and I'm just going to graph some points. So I have -3 and 0 and 1 and 0. Those are my x-intercepts. And then I have my y-intercept. And I don't have anything else as far as points, but where x is 3, I'm going to have a vertical asymptote. My slant asymptote, what I want to do is go to my calculator. If you wanted to, you could actually go to the second one and just type it in there, and -1/4. And sometimes you have to put a parentheses. And now if I go to graph, the red part, that is my slant asymptote. Go to second and table. You're looking at the red part. So you just want to find any points on there. So I see -3, -0.5. This is my asymptote. I'm just going to grab a point on the other side. So 7 and -3. Now I see that this part of my graph, I can connect the dots. I can get really close to my vertical asymptote. I can get really close to my slant asymptote. I just can't touch it. So I noticed I didn't have any points on the other side. So what I can do is go to my table, and on my table, what I'm looking for, and if it's going to confuse you, get rid of the red. I'm looking at the Y1 column. Anything that's after my vertical asymptote of 3. So any number that's after this error, I can go here. So like 5 and -4. We know it's in here. So anywhere in here, and it can get really close to the vertical, but it can't touch it. So when I'm looking at my end behavior, what I want to look at is the arrow that's closest to my slant asymptote this time. And I'm actually going towards negative infinity on my x-axis. So as x is approaching negative infinity, what's going on with that arrow? Let's go to the calculator, and then we're going to go to second window, second graph. So for negative, positive infinity. Why? Because the number is a big number and it's positive. So if I go to second window and I take that negative out, all I have to do is hit delete, go back to second graph. Now, if it's positive infinity, what's going to happen? And then it's showing me that it's a negative big number. So that's negative infinity.